So I just had a glance at these quiz questions. I'd like to take them up after we go through the lecture because the lecture covers that material, and we'll see if it follows from there. So if you have other questions, like about the homework, which this time I'm sorry to say is a little on the hard side, then that would be also a good thing to ask. Just put a question on Piazza. So today's lecture is easy, I think. About the exam, I'm almost done grading it, so you should have grades by tonight. I was hoping to have it done by this morning, but it didn't happen. All right, so so today's lecture is about implementing stacks and queues, and again, it's not that you'll ever implement a stack or a queue in your life. I mean, you can just use the pre-existing data structures, but they're very simple data structures, and it's just a good way of learning about how to implement things efficiently. So this is not the skill that we're trying to get at is to look at how do you implement data structures, how do you figure out which implementations are efficient. It's not the subject of this section to make you the world's best stack and queue implementors. Those people have been there 50 years ago, and so that's not really the interest. The interest is for you to learn from what these people have done and to be able to independently reason about how these implementations work. All right, so stack as a linked list. The purpose here is we want to be able to implement a stack as a singly linked list. And it seems plausible that we should be able to push a new node and we should be able to pop a node, and we want to do it in such a way that both adding a new node and removing a node are O of 1. And so my question to you is how to do this. So when you have this linked list, we are completely free to choose where we want to add nodes and where we want to remove them. We just, of course, need to make it so that it works out with the stack data structure, number one, and number two, that it's efficient. So, not wanting to give away the answer, but there's some places here where it's probably not so efficient to doing the adding and the removing because you have a singly linked list, and some of them where it's more efficient. So let me just set up the clicker question here. That's actually an interesting idea. Yes. All right, let's walk through this here. So, number one, push adds before first. That would be here, and pop removes last. Well, that's not going to work, right? Because pop needs to remove exactly what the last push put in there. So this is not compatible with what this stack is supposed to be, and for the same reason, number 4 is going to be out of the question. Push adds before first, pop removes first. That looks good because it does what a stack is supposed to do, and it can easily be done with O of 1, right? Because there's only one step to do. So the question is, what about number 3? Is it a viable option? Could you make it so that the top of the stack is the end? Now, adding at the end in a singly linked list is no particular problem. You can have a reference to the end node. But if you remember, removing the end from a linked list, from a singly linked list, is not efficient. So 3 isn't really going to work because the removing here is O of n. So 2 has got to be the answer. Now, you might say, so what? I'll just make it a doubly linked list. But if you think about it, if you have a way that works, and number 2 works, then there's no point in paying for the extra memory of the backlinks. So option 2 would be the preferred implementation. Now let's look at it with an array list. So we would now put all the values of the stack in an array. Once in a while, we push so many elements that we would have to grow the array. That's fine. We understand how to do that. And so we want to, and if we have lots of pops, we'll eventually want to shrink the array again, and we kind of know how to do that as well in an O of 1 amortized fashion. And so we'll keep track of how many elements we have. That's easy enough to do. That's just a counter. With every push you increment, with every pop you decrement. So the only thing that we need to resolve is, where do we put the top of the stack? Is the top of the stack, is it here at index 0, or is it here at the lastmost index? And again, that seems, I think, pretty easy. So let me just go into the question. Let me actually see how people were doing on this one here. So there was a non-trivial minority who picked 3 for some reason. So those 8 of you, have a look at why adding to the removing from the end is O of n of a linked list. All right, let's do. Oh, no, that's better. One, 2, 3, 4. Show the answers. Send it off. All right, so hopefully this one will go quickly. Let me show you the options. It's question 2. You'll figure it out. The second question 1 is question 2. So stack this time with an array. We just lost a vote. So again, when we go through this here, if we add, so here's the first element, and here's the last. If we add before the first and popping the last one, that's not going to work. We have to pop what we pushed. And so this one isn't going to work for the same reason. When we add before the first, that's really not going to work in an O of 1 fashion, because if you add something in an array here, all of the other stuff has to be moved down, and that's going to be O of n. So this is going to be out. And so by sheer elimination, it has to be 3. And 3, you can see that it's going to work in constant time, because you can add to the last element of an array list in constant time, because all you do is you access the field of index size and increment size. And similarly, removing the last one can be done in constant time. So this here is the right one. And so the thing to remember with an array list, the end is at your disposal in constant time. Just any of the other positions is not. All right, so that was easy. And so with the stack, really, there isn't much inherent interest. So let's turn to queues, where it gets to be a little bit more interesting. So queues can be represented both as linked lists and as arrays. With the arrays, as we'll see in a minute, there is an extra twist to it. Linked lists is still pretty straightforward, but now we do kind of have to worry, because we want to have a singly linked list so we don't have to pay for an extra round of pointers. And so it's not totally obvious to me anyway where one adds and where one removes. And you have the choice. Should this one be the head and this one be the tail? Or should this one be the tail and this one here be the head? So that's pretty much the choice that we have. So let's put up the thing. All right, so here we had an overwhelming winner. Good. All right. This one should still be pretty simple. All right, so let's again eliminate those that are incompatible with a queue. So a queue is last in, first out, is first in, first out. So with the queue, you want to add at one end and remove at the other, so that rules out this one and this one. And now let's see. So if we add before the first element and removing the last element, that'll work. So that way you would say this here would be the tail end of the queue, and this one will be the head, and it'll be a queue, all right. But the difficulty is you want to remove the head of the queue, and the last element in a singly linked list is expensive to remove. So you don't actually want this. So this one here is expensive to remove in a singly linked list. So if it's expensive to remove but cheap to add, well, hey, then our choice should be clear, right? Then this one should be the tail, because we added that at the tail, and this one should be the head. So we remove before first and add after last. That's this option here. Let's see. And so, okay, everyone's getting this. Great. Now, the only of these alternatives that's a little bit tricky to understand is if you implement a queue as an array. Now you might say, why do you even care about having two ways of implementing a queue? If we have a perfectly good one as a linked list, why even bother about the array? And the reason is that anytime that you have a linked list, it's a little bit expensive because you have to allocate storage for all of these extra links. And also each of the nodes is an independent object, and it takes a bit of effort for the runtime system to manage that. Now, in a program that you and I are writing, we don't really care, because that's the kinds of queues that we might be implementing. That kind of cost is a drop in the bucket to all the other stuff that we're going to be programming. But if you program something like on a smart card, where you care about every last byte, that thing might only have a few K of memory, and you would care. You would really not want to waste anything. And in that case, it's attractive to be able to use an array, because an array there's no links. You just store your raw data and nothing else. So it's a good question on, can you do a queue implementation in an array? Now, and that's not so simple, because if you do the obvious thing, it's not going to work. So the obvious thing would be to say, well, we'll add to the queue at the end. And then for removing, well, then you'd have to remove at the beginning. But if you remove this element, then all these other elements have to go one down, and that's an O of n operation. So the obvious idea of saying the tail is at the end and the head is at the beginning is going to make an expensive remove operation. And so we don't want that. But if you think about it, there is a slick way of doing it if you use the following idea, to say, well, instead of removing, why don't I just move up an index that tells me where the tail is? And the next one that gets removed, I simply move up this thing again. And so thereby, I don't actually physically need to move anything. And so that way you'll have two positions, the head position and the tail position, which I guess by sheer genius I reversed in this picture here. So let me go to the picture instead, where it's more consistent. So you keep two positions, and because I was confused what a head and a tail is. So you remove at the head and you insert at the tail. So it's exactly right the way I drew it. So the head index tells you where is the next element that you want to remove. The tail index tells you where is the next element that you want to add. And so you add here, you remove here, and something funny happens though when you get to the very end of when the tail now. So in this position here, now we want to add like another 4 elements. So the first element will go here. The second element will go here. And now you would say, well, with the third element, there's no room. So I have to grow the array. But actually, there is room. All of this stuff here is now unoccupied, so we might as well make use of it. And so it's called a circular array implementation, because we will boldly go and store more stuff in this unoccupied region. And so thereby, the contents of the queue is sometimes it's a contiguous area like this, and sometimes it breaks up into two pieces where it wraps around the end. And that just happened because the tail end just started wrapping around into what now is unoccupied area. And so the beauty of this is that adding and removing are both constant time, because what's involved in adding, you simply increment this index and you make a single store here, two operations. What's involved in removing, well, that's even cheaper. Removing simply means to increment this pointer. You don't even have to take it out. You just leave it there and don't look at it anymore. And you just update that pointer, constant time. Now here it says O of 1 plus. Why the plus? Because, of course, it could happen in theory, or in practice, it could happen that we have a lot of adds and not enough removes to keep up with it. And in that case, one is going to run out of space. It's going to wrap, and maybe, but at some point, all of the space here will be gone, and then you have no choice. You need to relocate and shovel everything into a bigger array. But we've dealt with that last time, and we've learned that that operation is still amortized O of 1 if you double the size of the array each time. All right, so that's the basic idea here, and it is kind of a clever idea if you think about it, to say, well, we're just going to we add more elements, add one here, and now instead of making a bigger array, just make use of the unused stuff over here. So let's practice that. So I want you to run through this code here, and that's going to take probably a sheet of paper. I don't think I could do this in my head. Run through this code here and tell me what is the contents of the buffer after these four loops. These four loops, in fact. So let me set it up. You guys can get some paper out. No, I have no tags. I want tags. All right, so start working through it. So we're adding in 8 numbers. So you add at the tail, so each time that you add, the tail moves one further to the right. So I'll just do them all, 5, 6, 7, 8. And now the tail points here. Now we remove 4 numbers. Removing simply means to increment the head. So now the head is, it's here. So, should I erase these numbers? Yes or no? No, I don't erase them because the way that remove is implemented, it simply says head plus plus. There's no benefit in erasing them, since eventually they'll be overwritten. All right, so now we're adding in another 8 numbers. So 1, 2, now we wrap around. I hope there's enough room. Now let's see what happens. 1, 2, 3, 4, 5, 6. Now what happens? Yeah? Yeah, now we need to resize the buffer. So that's unpleasant. But what do we do? So let me solve just for the heck of it. No, let's resize the buffer. So we resize the buffer, and before doing that, though, let's see what the answer is. Okay, and so 23 people got the right answer, because the answer now has to be something else. Right now our buffer gets to be twice as large. It's going to have 20 elements. So if we just want to know the answer, we're done. We have narrowed it down to something else. And it's a good thing that I put in something else, because I had totally forgotten that it filled up. But this has saved me. So now it resizes. And that's actually a good segue to look more carefully about how the resizing works. So right now, my buffer looks like this. It is completely full. My head position, that's where the next removal happens, is here. My tail position, that's where the next addition should have been happening, if I had space, is at the same location here. So now, how does resizing work? You get a buffer that's twice as large. And now the naive way of doing resizing would be to just copy the numbers in here. 3, 4, 5, 6, 5, 6, 7, 8, 1, 2. And then, but that's not going to work. Right, because now we have no room here. The room is at the wrong place. So we want this room to grow. We want it to come after the 6. So what you actually have to do when you resize is you have to completely rewrite the contents so that the head is here, 5, 6, 7, 8, 1, 2. So you have to move this block over here, and then you have to take the other block, 3, 4, 5, 6, over here. You put the tail position here. No, the head. I always mix up the head and the tail. You put the head here, because that's where you remove. You put the tail here. Now you're free to put in your 7 and your 8, and then the tail will be over here. Now to finish this, we've removed 4 more entries. That moves the tail to 1, 2, 3, 4 to over here. And so the contents of the buffer is 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. 0, 0, 0, 0, 0, 0. Where do those zeros come from? When you allocate a new array, and when we grew the array, we allocated one that was twice as large, it came pre-filled with zeros. In Java, whenever you allocate a new array, it gets pre-filled with zeros. So the appropriate answer of what's in the buffer is it's these 20 numbers. So notice that the 5, 6, 7, 8, these ones here, even though they have been removed from the buffer, they still stick in there. They're just old junk. Then we have the now consecutive stuff that of the actual contents of the queue, and then we just have a bunch of zeros that are also kind of junk. It doesn't really matter what they are; they're just in there. All right. So the important message about relocation, though, is that unlike with an array, when you relocate an array, you simply copy the array contents to corresponding positions. When you relocate a queue, you have to disentangle the queue to get all the elements back in order. Because you want the free space at the end of the queue where you can insert more stuff. You don't want to be in a position where both your head and tail point somewhere in the middle and then the room to grow is at the end. That doesn't work. So the cost of copying is the same thing because you copy n elements. You just copy a block of about some portion of them, and the other ones you copy in a second loop. The cost hasn't changed. All right, so the circular array implementation of a queue is definitely a trickier beast than the other three that we've seen, which are really pretty trivial. And did I have is there a homework question about this one? If not, I'll have to come up with one on the next one so that everyone gets familiar with it. It's an important data structure. All right, that's the end of the lecture. So I think you'll agree that the first three parts of the lecture were really pretty simple, and the last one had this the somewhat odd twist. All right, let's have a look at the lab. And here it is. So the purpose of this lab is to make you do some big O estimates, but do it in a more hands-on way, where you will actually run some programs, and where you hopefully kind of start feeling in your stomach what it means to for things to be faster or slower. So it starts out with an extremely simple program that just makes an array list. I could have used an array equally well. Adds numbers in it, and then it removes the first one. So that's the one that you know to be bad because everything else gets shifted over. So we're removing this one, and that means all these others are going to be shifted over. That goes on internally in the remove method. You don't see that, but nevertheless it does happen. And so when one runs this program, and I'm just going to run it really, really quickly. This program is so simple that it's easier to just compile and run it on the command line than to fire up NetBeans. So you should just do the same thing. Now I'll run it, and I'll have it with an array of 1,000. Well, that was instantaneous. It reports the last element that it removed, and because it removes them starting with the first one, the last one to be removed is going to be the last one inserted. Notice that I specify the length of the array on the command line. I just type it in here. Then that means it ends up in the args array, and then args0 is that string. I need to convert the string into an integer. I do that here. So let's do it with 10,000, with 100,000. That was a little longer. Let's do it with 1,000,000. That is more than 10 times longer. So I increased the size of the job by a factor of 10. Made the job 10 times bigger. And it now takes longer than 10 times to do it. Way longer than 10 times. And so that's something that you just kind of want to experience. So I'm killing it right now because I don't have that kind of patience. I might want to, instead of doing it with 1 million, I might want to do it with 500,000. Right now I'm doing it with 400,000. At some point, these things get so slow that you don't really want to do it in a lab because it's boring to just watch it. So the lab instructions tell you to kind of find a sweet spot for where the timing still makes sense. So now the next thing is, if you want to know how long something took, there's a nifty utility called time. And it just runs a program and it tells you how long it took. And it's part of Cygwin, and it's part of any bash shell. So I just want you to use that. That way you don't have to write the timing code in Java like we've done in chapter 14. So go through that with this experiment and then plot some of these numbers. That's all pretty easy. And then the next part, and I hope you're going to get into part B today and maybe even finish it, because it's very much like the question on the midterm. So one way of computing the median is as follows. You identify the largest value, which in this set of numbers would be what? 410. No, 418. Obviously, I'm not a realtor. 418. You identify the smallest one. This one. You remove them both, and you keep on going. Did I mess up? Okay. All right. Okay, you get the idea. And so you keep on going, and eventually you're going to be left over with either one number or with two. If you're left over with one number, that means you started with an odd number of items, and then that remainder is the median. Otherwise, you had an even number of items, and then you have to take the average, one plus the other over 2. So, and I want you to program this algorithm, which is really the one that I asked questions about in the exam, but this time you're actually going to be implementing it. And I gave you the basic outline of it, so you don't have to spend time with the boring part. Like here, I'm computing the average for you. And I want you to just use, so that you don't have to implement that stuff from scratch, just want you to use the methods that are in the API. There's a method for computing the maximum for the minimum, and it's easy enough to look that up. So and then I kind of want you to run it, and to get a feel for how the performance is by running it with larger and larger data sets. And now the way this algorithm works, as you've just seen, is it removes elements. But so let's say, which one was the largest one? This one here. Okay. So I've removed it. But if you think about it, removing is in a large array is wasteful. It's expensive. It means all of this other stuff has to be moved down. That's an O of n step. Instead of removing it, I could simply take this guy here and copy it over here and shrink the array down by 1. Shrinking an array down by 1 is an O of 1 operation because it doesn't involve any movement of anything. And copying one element is also an O of 1 operation. So since I don't care about the order of the elements, I just want to remove them one at a time until the median is left. I don't care about the order. It seems it would be cheaper, much cheaper, to instead of doing this thing. And it's going to be cheaper. So I'm going to make you implement that, and then you're going to compare the execution timing, and you're going to notice that the execution time did go down. If you give it in large enough array, you will notice that it was a genuine speedup. It might have gone down, when I tried it out at home, it got me from 23 seconds to 19 seconds or something like that. And then a larger set, from 100 seconds to 85 seconds or some such thing. So it definitely, that's time is money, so it's worth doing it. But it wasn't like a dramatic change. It wasn't 10 times as fast or something. And I want you to ponder why that is the case. There's a very rational explanation on why it's a worthwhile speed up, but why it didn't dramatically change it. And as you'll notice when you go through that, the big O efficiency didn't change. Then on Tuesday, we're going to be running off where we're going to go to a way of computing the median where the big O is dramatically different, and when you run it, you'll feel by just looking at the time on how it's a much better way of doing it. That way involves sorting, so it turns out that sorting is beneficial in this case. And then in the last part, it does seem to be kind of a waste to sort something when you don't care about the order of any but two elements. And so there is a way of computing the median without sorting that's actually kind of slick, and so that'll round out this lab. All right, so that's the lab. Let's get going, and hopefully you get done with the better part of B.